Hi, my name is Aaron Greenberg. I'm an undergraduate researcher at the University of Pittsburgh with Dr. Jeremy Levy's group, and I will be speaking today on the influence of temperature on lanthanum aluminate strontium titanate nanowire lifetimes. One of the things that really defines what we do in Dr. Levy's group is the devices that we create in the LaO system. On the left, you can see an example of a single electron transistor. In the center, a single electron transistor being used to measure surface acoustic waves, and on the right, a nanocross device. All of the devices are used by different members of our group in different ways to perform different experiments, but one of the things that all of them share in common is the technique that we use to create them, the conductive atomic force lithography technique. This technique works by applying a positive voltage to an AFM tip, and by dragging this positively biased tip across the surface of the sample, we're able to create conducting channels in the two-dimensional electron gas between the two substrates. By applying a negative voltage to the tip and dragging the negatively biased tip across somewhere where we've previously written with positive voltage, we're able to erase the writing. This erasure process is integral to the writing procedure in creating a device, as it allows us to selectively erase areas that we've written and create barriers in the devices to allow for things such as the single electron transistor. It is also worth noting that this writing and erasure process is repeatable and does not damage the sample. How does this conductive atomic force lithography technique work? That's through the water cycle mechanism. This mechanism that we use to describe the conductive AFM lithography is such that the water in the air adsorbs onto the LaO surface, and once it is there, it dissociates into H+ and OH-. The positively biased tip removes these OH- ions, leaving an excess of protons on the surface and producing a conducting interface. When we apply the negatively biased tip, it removes these excess protons and restores the insulating state. However, over time, the sample will also become unionized due to the ions present in the air. So we know that as a segment of wire is written, it begins to decay. Over here on the right, you can see an example of a previous test that we've done where we begin by writing a wire and measuring the conductance jump, and then you can see that it begins to decay here in air, and once we place it into vacuum, the decay is almost completely arrested, and once it's removed from vacuum, it begins to decay normally. So we see that we can slow this decay by placing the sample in a vacuum, and we know that the decay occurs over a timescale of hours. However, it's worth noting that this decay limits our ability to create complex devices. When we slow this decay, we can create the more complex devices, and these complex devices allow us to measure more interesting effects of the LaO system. So we want to create more stable samples and stable devices. In the past, we've taken measurements at 300 Kelvin and ambient pressure, and we know the lifespan of the devices is on the scale of hours. We've also taken measurements at around 80 Kelvin and close to 0 Kelvin with very low pressure at both points, and we see that the lifespan at these points is virtually infinite. However, we don't really understand what is going on in this big yellow area. We don't know how temperature affects the lifespan of our devices. So what I would like to do is replace this yellow area with the slightly smaller blue area, where I'm focusing primarily on what occurs above freezing. By looking at what happens above freezing, hopefully we will be able to extrapolate into the regime below freezing and really understand what happens with the lifespan of our devices. So how are we going to test this? We begin by drawing a device in the AFM. I'm drawing just a simple 4-terminal wire used to measure the conductance of the sample, and we then place this device into a cryostat. And it's worth noting that when we place it in the cryostat, we do not actually purge the cryostat. So the air that is in there when we insert the sample is the air that is in there for the entire test. We then vary the temperature in 1-hour intervals, as seen by this top figure here, and we measure the conductance as a function of time, and we can compare that to the temperature. So you see, when the temperature drops, there's a steep jump in conductance, and then it decays normally over the time where the temperature is stable. We then measure the slopes of the conductance, applying a linear fit due to the short time scales, and we then plot the slopes against temperature. And by themselves, these slopes aren't terribly useful, but we see that it's largely exponential. So we tried plotting the natural log of these slopes against the inverse of temperature in an Arrhenius plot. Now, the nice thing about an Arrhenius plot is that when we take a linear fit of this line, it yields an activation energy for the decay function, and that is 0.88 eV. We then took the average conductance over each time span and divided it by the slope to get the time scale of the decay of our nanowires. What we see here is that at 300 Kelvin, the time scale is about 1 day, but at 275 Kelvin, it's close to 25. So we have that cooling the sample by 25 Kelvin increases the lifespan of the device by 25 times. That's pretty remarkable, because that means a very small change that's very easy to do gives us drastic improvements to the lifespan, which will allow us to create drastically more complex devices. However, we'd like to take more data, we'd like to look further at this, and we'd like a more convenient way of cooling our samples than using the cryostat. So we purchased a thermoelectric cooler. And this thermoelectric cooler is really good for cooling your drinks. But it's not that good for cooling your samples because it has no real temperature control. You can select the power level, and these arbitrarily defined power levels, as created by the manufacturer, have some very large temperature variations of around 2 degrees Celsius or so. That's good for cooling your drinks, but we want more precision than that. So what we did is we took out all the electronics and we replaced them with our own control. We're using an Arduino to control the power level of the cooler, and we have our own external thermometer giving us more precision over the temperature of the sample there. This is a more convenient way to cool our samples, and it will be what we use to cool our samples for all of our tests here in the future. So what are we doing next? With this new cooler, we would like to take longer duration tests at a single temperature. Whereas with the first tests, we varied the temperature over time, with these tests, we'd like to keep it fixed at a specific temperature for 6, 7, 8 hours, or if not longer. One of the other things we would like to try is writing at a reduced temperature. Writing at a reduced temperature may impact the decay of the wires. It may just exhibit the same decay as cooling the sample, but it may also impact the conductivity jump. But it may also impact the conductance jump of the wires. This is something that we haven't tested, but we were thinking of ways that we would be able to cool our AFM in order to do these tests. And the conclusion that we came to is that the easiest way to do this would be to cool the entire room. However, this does mean that we're cooling the room that the AFM is in to just above freezing. And, well, that's going to be mildly uncomfortable. But, we can bundle up, as you see there, and, we make sacrifices in the name of science. So in summary, we have seen that cooling the sample by as little as 25 Kelvin extends the lifespan of the devices by as much as 25 times. We want to explore this more and understand it further. We want to understand where this activation energy comes from, how it impacts the decay, and how the temperature and the writing process are intimately linked. We also want to increase the lifespan of our devices, which will allow us to write the more complex devices. As I mentioned earlier, these more complex devices allow us to study more interesting effects of the LaO-STO interface. If we were not limited by the time it takes to draw devices, we're able to draw much larger, much more intricate, and much more interesting devices to measure things in the LaO-STO system. So that's it. Thank you for listening.